So I want to talk to you today about a project that we've been working on for a few years now called Zor. It is a modified version of Zen. As said, this is work done with the Zen maintainers at Citrix and with George and Pete, who maintain the mandatory access control module of Zen. So what I'm really talking to you about today is hosted virtualization platforms. There are tons of services that use these platforms today, and you don't know if you're using these platforms who you're going to run alongside. For example, you could be running alongside competing services. So why are these users willing to place so much trust into these platforms? Well, one reason we've been given is for their small code base. For example, Zen, which is used by Amazon, has only 280,000 lines of code. There's been a bunch of research in making these even smaller. But perhaps the more important observation is the narrow interface that the hypervisor offers to the guest VMs. This is one similar to the hardware. And what this lets us do is it's much easier to check and validate that the hypervisor is correct. So is this trust well placed? Let's ask CERT. We looked at all of the type 1 hypervisor vulnerabilities in CERT, and there were 38 against Zen. Many of these require local console access or remote exploits against guest VMs. But what we're really concerned about is vulnerabilities that you can launch from a guest VM running on the system against the rest of the system. And of these 23 of the 38 that fit into this category, only 2 are actually against the hypervisor. So this left us with one question. What the heck are the other 90%? So before we can answer this question, let's first look at how a virtualization platform works. We have the hypervisor. The hypervisor is responsible for isolation, scheduling, and memory management. But in order to run a commodity operating system on a full virtual machine, we have this smorgasbord of other functionality like device drivers, management tools, a communication mechanism. And there's this complex set of interdependent interfaces between all of these components. Typically, these service components all run within a single domain of trust, which is the control VM. In the case of Zen, this is called DOM0. So what this means is that if a user VM is attacked from outside and exploited, the attacker can then attempt to attack one of the service components inside, like a device driver, say the block device. From within that, they can interfere with the interface that component has with other VMs running on the system. Because it's in this monolithic domain of trust, the attacker can then break into the control VM and take over all the other services. But what's more worrying about this is that the hypervisor has a single privileged interface with the control VM and the hypervisor have the single privileged interface. And this lets it do things like manage devices, create and destroy VMs, and arbitrarily access the memory of any VM running on the system. So what this really means is that a compromise of any one of these service components could result in a compromise of the entire system. So is this really a concern? Well, it turns out that other 90% of the vulnerabilities we identified are against this control plane. So we felt it was time to address the elephant in the room that has largely been ignored in virtualization security research. So we tackle this problem in 3 ways. First, we isolate each of these services into a least privileged service VM. We then make the sharing between all of these components explicit so that we can reason about their interaction. And finally, we contain the scope of exploits in both space and time. In order to make our work more attractive to real-world deployments, we give ourselves a strict constraint. We can't reduce the functionality, performance, or maintainability of the system. So what we're really talking about is understanding and managing our exposure to risk in these environments. So as we said, looking back at our architecture diagram, we have all of these components running in the single monolithic domain of trust. So what we'd like to do is be able to isolate them in a meaningful way. Well, we're running this in a virtualization platform, so what we have is a strong isolation container, the virtual machine. Further, the hypervisor assigns privileges based along this VM boundary. In Zen, these services are typically processes or kernel device drivers, which makes them easy to extract into their own system. So this is exactly what we do. We put each of these components in its own virtual machine. However, the picture is a little more complicated. Many of these services are performing multiple tasks that require different levels of privilege. For example, for the management tools, most of the tools operate at the same level of privilege, except for one component, the builder. The builder must be able to access guest memory in order to set up the initial page tables. So we further subdivide these components based along these tasks and using the principle of least privilege. So now we have even more of these small service VMs. This work was partly motivated by work that has already been going on at Citrix. So what they've done in the past was they took the device emulation layer and identified that each guest requires its own emulation layer, so why not just put that in its own container and associate it only with the guest that needs it? So we also do this. Now that we have all of these components isolated, we can start to reason about the sharing between them in a meaningful way. For example, we can completely isolate two VMs running on the system. They now share no components, and there's no way to interact between these. So why would you want to have a configuration like this? Well, let's consider the case where we have these components sharing. User B gets exploited and launches an attack on the block device. The attacker can now interfere with the interface this has with the other guest VM, performing a denial of service or sending corrupt packets, potentially trying to exploit the user A's VM as well. Going back to our separated configuration, we see that when B gets exploited and attacks the block device, there's no way for it to interfere with what VM A is doing because they're completely isolated on the system. However, if you're running a virtualization platform as a service, you want to be able to take the full advantage of all the hardware you have, so there's going to be some sharing. You may offer users willing to pay more the ability to have this strong isolated separation, but in cases where there's sharing, you'd like to be able to reason about what the exposure to risk is for your consumers. So we add a secure audit mechanism where the hypervisor can write off into off-band or log in an external host. So the way this works is every configuration change you make, you write an entry into this log. So let's say we want to create a VM. We'll write a create message into our log, and then we instantiate the VM. Now we'll want to connect it to the network and block device, so we write these entries in and then create the connections. What this allows us to do now is, if the block device is compromised, the provider can ask meaningful questions of the log, like which VMs were relying on the block component when it was compromised. And the result is that B and C were. A is unaffected as it didn't use this component at all. An interesting property fell out of all this isolation that we got. Not only are they contained and can we reason what they're sharing, but we can now start to consider their temporal aspects. How long do these components run? Well, it turns out that similar components have similar temporal properties. So first, let's consider the platform devices. How exactly does a hypervisor bring the system up? Well, first we actually boot the hypervisor. It then loads some operating systems to bring up the system, initialize hardware, and then we launch all the other services. Once a system is running, however, we don't need these initial components. They contain a lot of privilege. If they can bring your system up, they can bring your system down. So we make the observation that because they're running in VMs, we can now dispose of them quite easily. This effectively removes all of that code and that privilege from the system while it's running. When we went to consider how to operate device drivers, we realized that we could use a technique found in high availability, that of micro reboots. In high availability, it's used to restore a component to a pristine state in order to avoid failure. However, this is a desired property for security as well. If we could restore components to a known good state, then we don't have to worry about if they've been exploited. However, the performance overhead of doing these micro reboots, while acceptable in a high availability circumstance, may not be applicable when we have these highly performant virtualization platforms. So instead, we designed our snapshot mechanism for Zen. The way this works is that you boot a VM and you let it run into the point where it's just about to process user requests. At this point, you take a very lightweight snapshot. Essentially, all we're doing is saving the CPU state. We could save the entire memory contents. However, this is expensive both in terms of time and in memory consumption. Instead, what we do is when we start processing user requests, We take advantage of a mechanism in Zen called log dirty. This is used by facilities such as Live Migrate. As the guest runs and memory is dirtied, we copy the original memory into the snapshot. When we're ready to reset the VM, we simply copy the contents back into the VM and reset its CPU state. We are now ready to continue processing requests. It turns out we can do this very, very efficiently. On a full Linux VM that is heavily loaded, we can do this as quick as in 4 to 25 milliseconds. When we applied this to the device drivers, we saw something interesting happening with the network device. We are still seeing network downtimes of 4 or 5 seconds. It turns out that if you're doing gigabit over copper, there's a specification that you have to auto-negotiate your link when it comes up. To solve this problem, we use another technique from high availability, the recovery box. The way a recovery box works is it gives you a small portion of memory that is resistant to the restart, so it doesn't get reset when we do these rollbacks. We can then store configuration details into this, for example, the link state, and when we reset the VM, we just pull the link state information out of this. Now that we've solved this problem, it turns out that we can restart these drivers fairly frequently. And in fact, we had them restarting as often as once per second. The management tools have an interesting property. They take a request, they process that request, and when they're done, all of that state that was generated between the time they processed that request was essentially temporary state just for their request. So if we could apply our snapshots to this, then we can effectively throw away all of that generated state, processing each request from a pristine version. So let's look at the builder as an example. We want to build a new VM, so we spawn this builder. It starts running, dirtying its memory, accesses the image from disk, and creates the VM. We can then destroy all of that temporary state, returning to our pristine image. When we want to launch another VM, we do the same thing. Spawn our new VM, generate our state, and then throw it away. What's interesting about this is that we have a shared service, but it's shared in a time-multiplexed way. That is, it's handling requests from multiple VMs, but only handles the request from one VM at a time. By doing these snapshots and rollbacks, we've effectively turned this shared component into a dedicated component for the requesting VM. We now have one component left that we haven't discussed yet, the IPC mechanism. In Zen, this is called Zen Store, and it proved. So before I describe exactly what we did, let's first discuss what Zen Store does. So Zen Store, which is Zen's version of the IPC, is a configuration repository. This stores things like the name of the VM, the amount of memory it has, and the configuration it has with other components on the system. Because of this, it is necessarily long-lived. You need all of that state to exist for as long as the system is running. So first, let's look at a typical interaction a VM might have with Zen Store. User B has a packet. It's shared a page. It's made a memory page available for the network driver to use, and it now needs to inform the network driver that it can map that page. For Zen Store to know that there's a packet waiting, it uses what's called an event channel, which is Zen's version of virtual interrupts. When it has a message ready, it triggers this interrupt, and Zen Store then knows there's a message. So the guest sends the message to Zen Store, which writes an entry into the repository and sends its reply. The network driver can now read this information out and know that it can map the page. Now let's consider a VM that is trying to exploit Zen Store. It sends a bad message and takes over Zen Store. It now has full control over the entire repository and owns this component for as long as the system is running. However, we noticed something with Zen Store. There were sort of two parts to it. There's the part that handles the processing, the actual logic, and there's this long-lived repository. And it's the long-lived repository that is the problem in trying to do restarts on Zen Store. So what we do is we take all of that long-lived state and we put it in its own VM. Now we have the request processing, the transaction management, and the access control checks running in the Zen Store logic component. So let's look again at a typical transaction. We send a message to Zen Store. It now forwards this on to the state component, which writes it into the repository and sends the reply. We leverage the hypervisor and monitor the interrupt channel between these VMs in order to know when the request-response pair is completed. Once it's completed, the hypervisor can now restart Zen Store and return it to a known good state. If the user attempts to exploit a vulnerability in Zen Store, it breaks into this component, and when the reply message is sent, the hypervisor resets it to a known good state. If the attacker is able to prevent that reply message being sent, the hypervisor handles this by maintaining a per-request watchdog timer. If the timer goes off, it means that the request hasn't completed in enough time, and it automatically restarts Zen Store. However, it may now be possible for the attacker to break into Zen Store and with that toehold of a one request, launch an attack on the state. For example, forging a message as a different VM saying, please shut me down. So to address this problem, we leverage the fact that we have these restarts and that we can monitor them externally. So we add this monitor component. The key observation here is that when we've reset Zen Store, we know it's in a known good state and it hasn't been compromised. So before we process any user data, we can tell the monitor, we see the packet, we get the interrupt, so we know it's there, but we haven't processed it, and we tell the monitor, I'm about to process VMB. Once this value has been set in the monitor, it cannot be reset by Zen Store. Any attempt to do so results in a restart. We process the packet, and in this case, the packet is from B and it was expected from B, so it goes through. Now if we consider our stepping stone attack, and when we reset Zen Store, it clears the monitor. At that point, we know it's back to a known good state, and the hypervisor can refresh that state and be ready for the next request. So now let's consider our attack. It sets B because we got the packet we saw a message waiting from B, so the monitor is now locked at B. Zen Store has been corrupted, and B wants to forge a packet from A. The monitor says, oh, that's from A, I was expecting a packet from B, I'm not going to accept it, and I'm going to cause Zen Store to get restarted, and we're back to a fresh copy. So in this diagram, the green area is that point where we know Zen Store hasn't been compromised and it hasn't processed any user data. We limit access, and from that point on, we don't trust Zen Store logic to be necessarily uncompromised. But because we've locked in that value in the monitor, we can guarantee that it can't interfere. So similar to how the builder and tools work, where we took a shared component and made it dedicated for each request, we've effectively taken this long-lived shared state and made it dedicated for each VM. So now what we've talked about is we've isolated all our components into their own VMs. This gives us the ability to have shared nothing configurations. When we do have sharing, we can reason about our exposure to risk. And we've considered the temporal properties of all these components and reduced them so they run for the minimum time necessary. So how does this fare on our system? We have 5 key questions. What do the privileges look like now? What is the impact on the security of the system? What are the overheads? What impact does isolation have on performance? And what impact do the restarts have on performance? So this is what our privilege graph looked like before. Every component effectively had every privilege. We've now reduced it to only those that they need. However, not all privileges are created equal. For example, a particularly scary one is the ability to access the memory of any guest on the system. Now only 2 components can do this. The first is the system boot, which we throw away after we've initialized the system. The second is the builder. To address the builder, we built our own tiny custom operating system specifically designed just to build VMs. So of those 21 vulnerabilities we identified against the control VM, we're able to contain 21 of them. So we may not fix the vulnerability, but we've contained it so it can't spread to the rest of the system. We've reduced the TCB from the control VM, which is typically Linux and Zen, which is 7.5 million lines of code, down to the builder, which is 13,500 lines of code. And both of these run on top of the Zen hypervisor. In terms of memory overhead, each component has a relatively small memory footprint, as it does only one thing. For the total, we've ignored the system boot and PCI config as we destroy these VMs and the memory is reclaimed by the system. A typical Zen install recommends that you give DOM0 768 megabytes of RAM. So before you think we're claiming that we give less memory, if we add more components in DOM0, the memory footprint remains relatively static. However, in our system, as we add more components, we need new VMs, which brings the memory footprint higher. But one interesting property we get out of this is that, say in DOM0, I have a process that gets into a bad state and starts consuming memory. It'll then cause the system to swap, affecting the performance of every other process. In our system, they're contained within their own VMs, so the process that gets into a bad state will only affect itself. To measure isolation, we did 2 tests. We did postmark and wget. The postmark is a standard array of configurations, and for wget, we fetched files to dev null to test the pure network performance and to disk to test the interaction between these components. The dark bars represent a standard Zen install, and the light bars represent Zor. So as you can see, for all of these tests, we remain on par with the Zen performance. To test our restarts, we decided to do a kernel build over NFS. The first bar is a standard Zen install, doing the kernel build over NFS, followed by Zor doing a kernel build over NFS. We then did driver restarts at the 10-second and 5-second granularity, and as you can see, the performance impact of this isn't that significant. So what I've talked to you about today is that components are a major source of risk in a virtualization platform in the control VM. These are responsible for 90% of the vulnerabilities identified in CERT. Our system isolates these components in both space and time, which allows it to contain the exploits and provides an explicit exposure to risk. We've done all of this while maintaining the functionality, performance, and maintainability of the system. And we're currently updating our patches to release to the open source Zen tree. Thank you.
I'm Stefan Sturry from Microsoft Research. So we were talking about sort of devices, and you said, a lot of their state I can actually isolate it, but, every device is there more complex. I have some shared state that I can reason about it if it's shared, and by disaggregating, I can actually make that reasoning more explicit. So the thing that I'm actually surprised is how there were sort of no bugs whatsoever in that shared components. All the bugs actually, sort of you're able to solve by disaggregating. So why is that?
Why is it there's no bugs?
Yeah, why is that there's really no bugs in anything that you actually left shared?
It's not that there's no bugs. We assume there's bugs, but we're not concerned with fixing all the bugs. What we're concerned with is, right, in the face of bugs, can we contain what the vulnerability lets the attacker do?
Hi, I'm Bernard Blackham from the University of New South Wales. I noticed in the graphs of disk performance, you actually had increased performance for wget to disk.
Yes.
I noticed in the paper you said that was because of performance isolation. Can you elaborate on that at all? Because it's kind of cool.
Yeah, so in the standard Zen install, because these are all running within the same VM, there's more interaction between the two components, whereas by disaggregating them to their own, they run with their own schedulers and they can manage their own time and potentially run on completely isolated CPUs. So this was an interesting artifact that we saw. We don't know how much weight to put on it in terms of a highly shared system, but it was fun.
So in theory, you could probably get those gains from pure unvirtual, normal Zen as well.
If you configured your resources, I'm sure you could. Yeah.
Alec Wallman from Microsoft. I had two quick questions. The first is I wanted to just make sure I understood your sharing model.
Okay.
In terms of, specifically for device drivers, do I have to have multiple physical devices? If I want to isolate the device drivers for different guest VMs, do I have to have multiple physical devices in order to be able to accomplish that?
Essentially, so you either have to have multiple physical devices or have a way to virtualize the hardware like they have now.
Okay.
Yeah.
All right. And then in terms of rolling back device drivers, do you have to issue an actual reset for the device state, for the device itself, after you've done the rollback, or no?
Yeah, so if we just roll back the software, not the hardware, then they're not agreeing on their state. So yes, when we recover from the rollback, we reinitialize the hardware.
Okay, so are you worried that if you're rolling back the hardware once a second, that the cost of device resets might actually be substantial?
It can be, and certainly once you get very frequent, you notice the performance impact more, and we're looking at ways to try to reduce that bring-up time.
Okay, thanks.
Okay, no more questions?